that I can introduce the next speaker, which is Cyril Briquet, and he will tell you something about diffing XML documents.
So good afternoon, everyone. The title of this presentation is Tagdiff, a diffing tool for highlighting differences in the tagging of text-oriented XML documents, which already says a lot of things about the presentation. The contents of the presentation are as follows. I will talk a bit about text-oriented XML documents and the motivating use case behind our work. I will then tell what Tagdiff is and compare it to other diffing tools, such as the well-known Unix command line utility, diff, and existing XML tools. I will then describe the algorithm, discuss a bit about its performance, and then I will conclude. XML documents are typically classified as structure-oriented or text-oriented. In the structure-oriented XML documents, in many applications, XML documents can be treated as unordered trees. Only ancestor relationships are significant, while the left-right order among siblings is not significant. Use cases typically rely on XML documents to store more or less structured data. For text-oriented XML documents, XML is relied upon to tag selection of text. What's in literal proximity is here important. Use cases include literary text, linguistic data, news, and so on. And we're interested in text-oriented XML documents. Our use case was the algorithmic tagging of a linguistic data corpus, a French dictionary. Multiple processing steps were involved. There's a sequence of 40 tagging algorithms of varying complexity. To validate the algorithms, it's useful to visualize, firstly, data before and after applying a given tagging algorithm. So the question here is the new tagging correct and complete? And it's also useful to visualize, secondly, data output by a reference version of a faster or more readable version of an algorithm. The question here is it the same tagging? So we wanted a command line tool to do exact diffing between XML documents. When I say exact diffing, this is at the character level, so it's not word by word or node by node. We really wanted exact diffing like in diff. We don't need options such as filtering out some types of information like white space, comments, etc. It's not a goal for us to merge or to patch documents, as do many diffing tools. But it's very important that the output is easy to visualize and to process by other command line tools, such as grep or Perl. And we don't need a graphical user interface. So the first thing we tried was to see how diff could be useful for us. It's a well-known Unix command line tool, and it's based on the classic diffing algorithm, the Myers 86 algorithm. However, diff focuses on differences between short lines, for instance, source code, and it does a great job. But when the lines are longer, and when it's packed with different types of information, such as text and text, it becomes less obvious to see the differences found by diff. In this small example, there are 4 differences, but they do not stand out at all. You've got 2 opening B tags and 2 closing B tags that were added into the below paragraph. So we decided to do our own version of diffing. We call it Tagdiff, and it offers vertical, segmented, and typed diffing. Vertical diffing because 2 documents are displayed next to one another into 2 columns. The differences are highlighted by the 5-letter symbol, angle bracket, 3- angle bracket, and the equal segments are marked by an equal symbol. So Tagdiff does segmented diffing. As you can see here, the documents are not showed as is or as big blobs of undifferentiated text. The documents are split into small segments. I'm going to take another example to show you what I mean by typed diffing. You see here in the left document a chunk of text in place algorithm, and in the right document an opening B tag, a text chunk, and a closing B tag. And what we want is to have the text chunk matched with the differing text chunk, not with the opening tag chunk. So we want alignment based on segment types. I'm coming back to diff for a second. Diff has a -y flag, an option, to output data in 2 columns. But there's no segmentation of long lines, only truncation, as you can see here, for example, for the left document. Also, all the contents are displayed. There is no specific contextualization of the differences, which makes it harder to visualize the differences. I'm going to talk a bit about 2 existing XML tools, DeltaXML XML Compare and Oxygen XML Editor. I'm not a user of either, so I had to go to the public websites. There is no alignment in the same sense that we showed you on the Tagdiff slide. For example, in DeltaXML, you see the piece of work and in-place algorithm example. It indicates that what's on the right side is between the first and the second word of the text chunk in the left side, instead of matching the text chunk together. For the Oxygen XML Editor, we think there's also the same kind of problem. And you have here in very pale color, very pale red, you've got the correspondence matching between the 2 documents, but they're not vertically aligned either. Only the currently selected difference is vertically aligned. So now that I've told you what Tagdiff is and what are some differences with other diffing tools, I'm going to describe the algorithm behind it. The main idea is to segment the XML documents into small type segments that are easy to align, easy to compare, and easy to visualize. There are 3 main phases in the algorithm. The first phase is diffing the raw text versions of the XML documents. The second phase is XML parsing and segmentation of the documents. And the third phase is the aligning of sequences of the differing type segment. We have implemented the algorithm in Java 8. It's about 5,000 lines of code to give an idea of how small or large it is. It relies on several libraries for the raw text diffing algorithm and for the way we store data into memory, so the XML data model. For the first phase of the algorithm, the diffing of the raw text versions, we use the classic diffing algorithm, the Myers-86 algorithm. It identifies which sections of the raw text versions of the 2 XML documents are equal and which ones are differing. We measured performance and found it to be slow for a large number of differences. Clearly, an optimization was required. But this algorithm is state of the art. It's recognized as such, and we are using a library that is said to be a high-performance library. So it was difficult to optimize either the algorithm or its implementation. So what we did was to optimize the use of the algorithm, how the algorithm is used. So we decided to split the two XML documents into many short sections with only a limited number of differences in each section, so that the myers-86 algorithm performance remains good. The question is, which splitting points do we choose? They must match in the two documents, otherwise the diffing would be incorrect. We choose as the default splitting points paragraph boundaries, which are often present in text-oriented XML documents. But the user can easily specify a regular expression to define other splitting points if it is needed for their documents. Well, the bottom of the slide here is not displayed, but the example I want to show is diffing is not done one time for the whole document, but many times in between and outside of the P and /P tags. Now that is done, we are going to look into the second phase of the algorithm, XML parsing and segmentation of the XML documents. XML parsing is currently done with SACS, but it could be done with DOM. It's a matter of implementation here. Importantly, no schema is required and no validation is performed. It enables to find differences in not valid documents. Because remember our use case, we want to validate tagging algorithms, and sometimes they can produce non-valid documents. And we want to see all the differences and not to have a validation error that stops the validation process when it finds an error. To store data into memory, we've chosen a chunk-based data model. It's not DOM, it's not XDM. It relies on some of our previous work, but it's very basic. Opening, empty, or closing tags are stored each as one XML chunk. When you take an XML element, it is stored as an opening tag chunk, many chunks for the children element, and a closing tag chunk. A detail, the end of lines are materialized as processing instruction. It's a design choice. It could be something else. And this is also stored as one XML chunk. In the example, in the small example here, after the XMLPrague, you see one end of line, the opening tag of the root element, two end of lines, p tag, and a text chunk. We want to do, after parsing, segmentation, which means taking each of the XML chunk and associated it with a diffing type and an offset. And we call that a typed segment. Type is a word that does not mean as much as it is, for example, for the XDM data model. It's very simple. The ATAP values that are defined are equal text, tag, processing extraction or command, and differing text, differing tag, differing processing instruction, and differing command. This information, the typing of each chunk, is given by the previous phase of the algorithm, the diffing of the raw text version. And now the offset we want to associate with each type segment are the offset in the equal data version of the XML documents. I mean, this is the part of the XML document that is common, that is equal between the documents with all differing data removed. If you have an offset in this version of the documents, you can align immediately the equal data part of the document. It also means that the type segments of a differing type don't have an offset. An example here where you see the typed segments. the XML prologue, which has been split because it is too long into 2 segments. On end of line, the opening tag of the root element of the document, which is differing from the other document in this example, and so on. Now the first phase, the alignment of equal data and the alignment of differing data. For aligning the equal data, the first phase we do is to group together in a sequence the neighboring differing segments. So in the example here, you see that the 3 differing type segments are grouped together in the same sequence, sequence j plus 1, with sequence j and j plus 2 being equal data sequences. The sequences of equal data have an offset in the equal data version and therefore can be aligned with one another pretty easily. Sequence I and sequence j are aligned based on the offset. Same thing for sequence I plus 2 and j plus 2. But you will notice that with this framing of things, with this structuring of the data, there's a strict alternation of equal data and differing data sequences in the documents. Therefore, sequences of differing data, like sequence I plus 1 and j plus 1, are also implicitly aligned with one another because what's before and what's after are already aligned. But the question that remains is that differing data sequences still need alignment within sequences. So if nothing is done, if no alignment is done, we'll have the text chunk aligned with opening B tag. We have here a combinatorial alignment problem to be solved for each matching pair of differing sequences. So what we do is systematic recursive enumeration of all possible alignments, which is brute force. But we do pruning of unpromising solutions to boost performance. The optimization algorithm is to take the alignment among all possible alignment with the lowest cost. Without entering into too much detail, the cost of 2 type segments of the same type and equal data is less than the cost of 2 type segments of the same type and differing data, which is less than the cost of 1 type segment matched with 1 gap. And this is less than the cost of 2 type segments of differing types. I'm now going to talk a bit about the performance of Tagdiff on a small test corpus, because Tagdiff is very recent, very new. We don't have many evaluations to talk about. We are testing on 3 pairs of documents, a pair of small documents, 14 lines each. It is a running example of this presentation. And we are also taking 2 pairs of medium XML documents, 1,000 and 4,000 lines each, respectively. And when you see the number of differences, it's roughly, grossly, 1 difference per line of the XML files, which is already a high number. On this graphic, on the horizontal axis, you see the 3 pairs of documents, small, medium 1, and medium 2. On the vertical axis, you see the runtime in milliseconds of Tagdiff. The upper of the 4 curves, this one, is for the unoptimized version of the algorithm on a slow computer. When I mean unoptimized, this is without the splitting that is done for the Myers-86 algorithm that I talked about at the beginning of the description of the algorithm. So unoptimized versions, slow computers, about 80 seconds. 40 seconds for a fast computer with a still unoptimized version of the algorithm. But with the optimized version of the algorithm, we arrive at 12 seconds for a slow computer and 5 seconds, roughly, for a fast computer. And when we apply Tagdiff to the small documents, of course, it's only a few hundred milliseconds. I will now conclude. I have told you about Tagdiff, which is a command line tool for diffing text-oriented XML documents where no schema is required and where no validation is performed. Visualization is vertical, segmented, and typed. Tagdiff relies on an optimized use of the classic diffing algorithm, the Myers 86 algorithm, and Tagdiff relies on alignment done by an optimization algorithm, which we think could be integrated into existing XML tools. The optimization algorithm is applied to many small sequences of typed segments that are easy to align, to compare, and to visualize. So that's it for the presentation. Thank you very much.
So thank you very much, Cyril. We have time for questions, but not yet for price offers from tool vendors who would like to improve their diffing. So there was one question over there, and from George.
Very impressive, thank you. Is there a place where we can download this, or is this for sale?
I don't hear you clearly.
Is this tool available as open source, or?
Not yet. We intend to open source it, but it's not yet publicly available.
Because I think I have a very good use for it. Thank you.
Hi, George Bina from Oxygen. As you mentioned, we also implement diff support. But when you have a diff, you specify that you try to do kind of an alignment. In our case, we do like a second level diff. Have you considered that, or will you do the same? So basically, the modified bits,
yes,
we apply the same algorithm again, more or less.
Well,
on that part to align them.
So I haven't thought about Oxygen Editor, but we can do the secondary diff with the alignment part of the algorithm, if this is what you're asking.
Yeah, so when you had a diff, you said you have a combinatorial problem, and
yes,
because you need to align those, what's in there and so on. In our case, I said we applied the same diff algorithm again, maybe
yes,
at a different level, like words rather than structure, for instance, or something like that, to align them. And that's maybe, if you don't do that, maybe it's something that you can consider because, you know, it's the same problem basically at a different level.
Yes.
Okay. Still have time for one question. Okay, so I don't see anyone else, so thank you again.